Yeah, so hello everybody. Welcome back from spring break to the Orbital Sciences Colloquium. It's actually very exciting to see so many here. I can guess why this is actually. But yeah, so we start the new series of the Optical Sciences Colloquium after spring break with a bang. So today we have Professor Katie Bouman here. Katie is an assistant professor in ECE, mathematical sciences and astronomy at Caltech. And I have to say that her work impressively combines the ideas from physics, signal processing, computer vision, and machine vision. And before joining Caltech, Katie was a postdoc at the Harvard Smithsonian Center for Astrophysics, and she received her PhD in electrical engineering and computer science at MIT. Katie has, of course, many awards, much too many for me to name them all here. But just to name a few, so she's the Rosenberg Scholar. She received the Royal Photographic Society Progress Medal. She is the Electronic Imaging Scientist of the Year. And she is a co-recipient of the Breakthrough Prize in Fundamental Physics. So the function that Katie is probably best known for is her co-lead on the imaging working group of the Event Horizon Telescope collaboration. And this actually led to the first imaging of the M87 and Sagittarius A black hole. However, I have to say that I personally know, or I personally can tell that Katie has a lot of other very cool projects going on in her group. I don't know if you have time to talk about this today.
I'm framing everything with black holes, which
so maybe a little bit, but Katie, know that you are always welcome here and that you can always come back. Yeah, Katie, we are very excited to have you here today. I hand the mic to you now, and the stage is yours.
Thank you so much for the kind introduction, and thanks so much for inviting me. I'm so excited to be here. This is my second visit. I came before to work with some of my colleagues here on the Event Horizon Telescope project. But it's like such a beautiful campus, so I'm excited to be back. So yeah, today I'm going to be talking about capturing our own Milky Way's dynamic black hole. So if you go out past the bright city lights tonight, you may see like the stunning view of the Milky Way galaxy. And if we could travel past millions of stars, 27,000 light years towards the heart of our spiraling Milky Way, we would eventually reach these cluster of stars right at the center. And by peering past all this galactic dust with infrared telescopes, astronomers have watched these stars over decades. And what they see is really quite remarkable. So by tracking the motions of the stars over time, astronomers have concluded that laying within their orbits has to be a compact object with a mass equivalent to 4 million of our suns. In fact, this discovery led to the Nobel Prize in Physics back in 2020 for the work of Andrea Ghez and Reinhard Genzel for the discovery of a supermassive compact object at the heart of our galaxy. And so for many years, people have thought that this compact object is likely to be a black hole. But at the distance these stars are orbiting, we still couldn't say for sure. And to study it and to build our confidence, if this is a black hole, we had to zoom in over 1,000 times closer. And there, Einstein's theory of general relativity makes some really exciting predictions for what we should see. So light propagating near a black hole doesn't follow straight lines. It's curved because the black hole is actually bending space-time. And so light moves around in curves and even can go in complete circles around it. And so what happens is around the black hole, we have this hot gas spinning around. And some of these photons are flying out and they fall into the black hole, but other ones just graze it such that the net effect is that the black hole bends them into this circular shape, such that the black hole casts this shadow on the backdrop of surrounding emission that's almost perfectly circular. And we call this the black hole shadow here. But this ring doesn't just take on any size and shape. If Einstein was right about general relativity, and the past astronomers were right about that being a black hole, that 4 million solar mass compact object being a black hole, then we would see a ring of roughly 50 microarc seconds with not a lot of wiggle room. And so after many decades of studying this mysterious object, back in May of 2022, we revealed the first image of this massive body, an image that perfectly lined up with these previous predictions from prior observations and theory. And so this is the very first picture of the black hole in the heart of our own Milky Way galaxy, a radio source called Sagittarius A star, or we call it Sag A star for short. And taking this picture took this Earth-sized telescope and an Earth-sized team, which I'll talk a little bit more about. But first, why was it so hard? Well, the fundamental challenge comes down to scale. Because the Sag A star black hole is so massive, it occupies roughly the size of Mercury's orbit around the sun. And that might sound large, but at a distance of 27,000 light years away from us, this is like trying to take a picture of a single grain of sand. But if this grain of sand is in New York and I was viewing it from where I'm coming from in the LA area. And so taking a picture of something that small required this international collaborations of scientists from around the world building new instruments and algorithms to make it possible. And many of those people were actually from here, University of Arizona. So some of them here in the audience today, CK, Jan, Dan Maroney, and Remo Talanis, among many other people here at the University of Arizona, are part of this team that has kind of made this picture possible. So today I want to tell a very abridged story of how we were able to take a picture of this black hole. But at this point, you might also be saying to yourself, well, am I feeling some deja vu? Did I see this picture before? And if I turn this picture around, it might look a lot like another image that you may have seen a few years earlier. And so this is the first image of a black hole ever produced, actually, that our own Event Horizon Telescope collaboration published back in 2019. But this is not of the black hole in the center of our Milky Way galaxy, but instead a galaxy called M87, which is 55 million light years away from Earth. But as I said, we published this image of Sag A star in 2022, and the M87 one 3 years earlier. But both images actually were recovered from data collected in the exact same week of 2017. So some of the questions I want to answer today is not just how do we capture a picture of a black hole, but also why was imaging Sag A star so much more difficult? And I'll first go through some of the background of black hole imaging, but I think it's really important to go through that a little bit so that you understand how the challenges of black hole imaging first, and then that will lead to two projects that I'll talk about for the future of black hole imaging. And these are two methods currently being pursued by and developed by my group at Caltech to push the imaging of black holes further to see things that are still currently invisible to us. So in particular, I'll be talking today about new machine learning approaches my group are developing for recovering the evolving environment around the Sag A star black hole, even in 3 dimensions. Okay, so let's get started. So again, why is taking a picture of that black hole so difficult? Well, because the black hole, that ring that I talked about, is so small in the sky, and we actually can only see it at a particular wavelength. If you plug this into the diffraction limit equation, it tells us to take a picture of that black hole, we need to build a telescope 13 million meters in size. 13 million meters is essentially the size of the Earth. And although we can't build a single dish telescope the size of the Earth, instead, the Event Horizon Telescope collaboration spent well over a decade joining telescopes from around the world to build a computational telescope the size of the Earth, capable of resolving structure on the scale of a black hole's event horizon for the first time. So how does this computational telescope work? Well, unlike with a camera, in the Event Horizon Telescope, we don't capture the picture in pixel space, but instead in its frequency space. So we are essentially going to be taking measurements of the black hole image's Fourier transform. And if we put telescopes all over the Earth, we would capture all the measurements we need of the Fourier transform to recover back the picture. But since we only have telescopes at a few locations, we only get a sparse number of measurements. And so it turns out for every 2 telescopes in our telescope array, we get a single measurement of the underlying image's 2D spatial frequency that's related to the projected baseline between the telescopes. So this is an interferometric approach that allows us to do that. But that means if we only have a small number of telescopes, then we only get a small number of Fourier measurements. But luckily, as the Earth rotates, we obtain other measurements. So since the projected baseline between the telescopes change as the Earth rotates, this amounts to carving out these different elliptical paths in that spatial frequency plane. So how do we actually make an image then after extracting these measurements? Well, at this point, we have the data. We can kind of abstract away the astrophysics of the problem and just think of it as a purely mathematical inverse problem. We have this sparse data, and our goal is to find the image that caused it. And if we had telescopes all across the globe and we measured all the spatial frequency measurements, this could, in the presence of no noise, this would be trivial because we would just need to apply the inverse Fourier transform. But since we only see a few samples, that means that there are an infinite number of possible images that are perfectly consistent with the data that we measure. And on top of that, the fact that we have a different and quickly changing atmosphere above each of the telescopes causes our data to be very, very noisy. For those of you familiar with like phase retrieval problems, here we lose our phase of our measurements because of the atmosphere. And this causes our problem to be even more ill-posed. But of the images that are consistent with the measured data, there are some images that we consider to have properties that we think are more likely than others. For instance, we'll say, oh, we want the image to be smooth, or we want the image to be compact in its structure. And thus our goal becomes not just to find an image that fits the data, but also one that looks like an image that we think is likely under some sort of mathematical model of a likely image. And so by injecting these kind of preferences for different image statistics into the pipeline, we can use this information to whittle down from those infinite possibilities to one image that fits the data, but is also likely under our image model. And so now, okay, in a totally hand-wavy way, I've told you how we can go from these sparse, noisy measurements to a single image. But how do we actually write that more formally? I just want to show you this because this will come a little bit handy later, but I don't want you to get lost in the math. I'll walk through this. So we're going to be solving an optimization problem where we're trying to find an image X here that maximizes the posterior probability conditioned on the measurements Y. And by simply rewriting this using Bayes' rule, we can see that maximizing this log posterior probability is equivalent to maximizing the log likelihood and some log prior term. So these are those two terms that I just really discussed in that totally hand-wavy way, right? The first one being the data fit, and the second one here being like how likely is your image, irrespective of the data. But note that even if we can develop methods such as these to recover a single image from this noisy data, we always have to be really cautious. And that's because any method we come up with, whether it's a regularized maximum likelihood approach like I'm showing here, or some fancy new machine learning approach, it's always going to have to inject some sort of information about what the image looked like to recover something back in the end. In this case, it's through that log image prior here, highlighted in yellow. And this injection of additional information is always going to bias our final image. And so, for instance, we didn't want to go into the imaging and have a preferences for images that have rings in it and then be super excited that we got a ring back in the end. And so we had to be really careful. And that meant the big question we faced in dealing with the black hole image data was not only just how to make an image, but how do we verify that what we're reconstructing is actually real, is actually the true underlying source. And we therefore tackled the imaging through this multi-step process, a process that included many synthetic data tests, strict blind imaging procedures, and like objective learning of these imaging parameters that we had to use and see how that actually affected the images that we got out. But actually nearly everything I've said so far holds true also for that M87 black hole that we published back in 2019. So, and that procedure allowed us to recover this image that we were very confident of. So we got that same ring under all different kinds of parameters, and we published this a lot earlier than the Sagittarius A one. So again, what made the Sagittarius A black hole data that much harder? Well, Sagittarius A is much closer to us. Remember, it's in our own Milky Way galaxy. And so that means that even though the black holes actually appear about the same size to us on the sky, if you actually factor in their physical distance, this M87 black hole is much, much larger than the Sagittarius A1. And so that means around each of these black holes, we have this hot gas spinning around, and that gas is moving at roughly the same speed. But just because Sagittarius A is physically a much smaller black hole, it has to move a smaller distance. And therefore, in the same amount of time, there's a lot more motion of the gas moving around the black hole. And so why is that so challenging? Well, that means that as we're collecting data, as the Earth is rotating, the material is swirling around the black hole so quickly that Sagittarius star's appearance is changing from minute to minute. So rather than all the measurements that we make over the course of a night, all pointing to the exact same image in the sky, instead, now, as was the case for M87, for Sagittarius star, now every measurement we make is coming from a different snapshot of the black hole video. And so we can't simply throw all these measurements in the same pot and try to say, just solve for one image that fits all those measurements. And so now not only do we have to deal with sparsity and noise, but now our algorithms also have to incorporate some way of dealing with that time variability, how to deal with that evolution. And we had to build different types of evolution models into the reconstruction process. And each of these decisions, the ones that prefer different images, the time variability types of decisions, all of these are going to bias our final image in the end. So how should we go about getting the range of possible Sagittarius star appearances? Well, to do this, we developed a number of different imaging pipelines. These pipelines have hyperparameters in them that are typically tuned by a human user, but instead of having a human tune them, we instead surveyed nearly 175,000 different hyperparameter settings and saw how those settings affected the images that we got out. So for instance, we generated data as if the Event Horizon Telescope were seeing a disk on the sky with no hole in the center. We made synthetic data, and then we saw what imaging parameters of our methods allows us to recover that disk shape. And then once we had figured out which parameters work best, we would transfer these onto the real Sagittarius star data and then see what we got out in the end. But we didn't just do this for one disk shape, but for a bunch of different geometric source structures that we thought could trick us up. And once we had identified a collection of imaging parameters that performed well across all these different synthetic data tests, then we would apply them to the Sagittarius star data to see the range of possible appearances. And when we did that, this is what we saw. So we saw this huge collection of different types of images. Each of these images you see is actually consistent with the Event Horizon Telescope data, but as you'll notice, they are all a little bit different from one another. So to emphasize the common features appearing in most of them, we could average them all together to see what kind of common structures come out. And when we did this, we get that ring structure that I showed at the beginning, this ring structure that aligned kind of with what we had predicted from prior observations and theory. And that really pops out. But it's also important to note that not all of the possible images looked alike. In fact, we found that we could cluster the recovered images into 4 categories based on similar visual features. And 3 of the clusters corresponded to rings, but where the brightness around the ring kind of differed. Exactly what part was the brightest around the ring. And then there was a 4th cluster that didn't look like rings at all. And so you might ask, how many were rings versus not rings? Well, the majority of them were rings. So about 98% of them were rings, and only about 2% of them appeared that we could recover appeared not to have a ring-like structure. So this fact, along with a number of other tests that I don't have time to get into, gave us confidence that that the Event Horizon Telescope data shows at least compelling evidence for an image that is dominated by a bright ring of emission. And this is, and even perhaps more exciting than this, is that the recovered ring that we had gotten, if it was that ring shape, the recovered ring perfectly aligned with that prior observation and theory, as I said. So 2 completely different views of the black hole, one that relied on the motion of stars and one that relies on the bending of light here, aligned exactly. And that was like kind of a wonderful kind of validation of general relativity. But even further than just testing general relativity, we find that by comparing this picture to simulations scientists have made for years, that the image we've taken is incredibly consistent with a number of these predictions. But that being said, there still were some surprises. So remember how I said that this black hole, it's evolving over time, right? So we found that the models that computational astrophysicists had developed seemed to overpredict how much it was how much evolution we were seeing. Sagittarius star was still moving and burbling around for sure, but not as rapidly as we kind of had seen in these computational simulations. And so we'd love to be able to image the actual variations around Sagittarius star to understand what our differences are in our model versus what is actually happening in reality. But doing this is really difficult. Why? Well, again, remember that the data we use to recover the black hole is actually being taken over an entire night. As the Earth is rotating, we get different measurements that together were used to make that M87 image. But since Sagittarius star is evolving over the time span of just minutes, that means every measurement is coming from a different snapshot of that black hole video. So how should we capture that black hole's evolution? Well, if we were just to apply the same static imaging technique on every just snapshot of time, there's just not enough data. There's not enough telescopes or projected baselines at any instant to get a reasonable image, and you'll just kind of get junk out. So clearly a naive approach like snapshot imaging isn't going to work in this case. So there are two ways that we can get around this problem in order to recover the evolving structure. First is that we could add new telescopes to increase the number of measurements coverage that we have. And actually, we're in the process of building what we're calling a next generation event horizon telescope, or NGHT. Among others, we're in the process of adding a telescope at the Caltech's Owens Valley Radio Observatory site. University of Arizona is actually one of the big players in helping to expand the EHT with the next generation EHT in the future. And so adding a lot of telescope dishes could help in our quest to make a video of the gas falling into the black hole by just filling up that measurement coverage more. But this on its own still isn't likely to be enough. So to solve the problem, the second thing we need to do is add structure into the computational reconstruction problem. So just as we needed to impose different kinds of image structural constraints to recover an image before, in order to recover temporal information, we'll also probably have to use information that ties information together in time. And so how should we go about doing that? Well, in my group, we like to think about all the different possible methods that we could do as laying kind of on a spectrum of increasingly strong assumptions about the structure. So we like to kind of move along the spectrum, having really weak constraints like we did with just the pure imaging that I talked about before, but increasing our constraints too, and see as we move along that can we extract more information, of course, under the knowledge that you are building in a lot more assumptions when you're doing that. So today I'll talk about two of these recent methods from my group that I placed kind of on opposite ends of the spectrum. First, I'll talk about how we're doing video reconstruction by using what I think are a relatively weak assumption. So basically all we're going to be assuming is that there is some shared structure over time. I don't know what that structure looks like, nothing at all. I don't want to build anything about what the structure is. I just know it's shared over time. And then also I'll show that if you are willing to make stronger assumptions, for instance, assumptions about do we trust general relativity or the emission model for how the emitting gas, how the gas is emitting around the black hole, then we can do things, even jump out of the 2D image plane and recover movies even in 3 dimensions. Okay, so I'll start talking about the weaker of these two approaches, video reconstruction, by assuming a shared image structure. And this work is led by my grad student, Angela Gao, postdoc Oscar Leong, and also Yvette Lin was a former Caltech undergrad who also worked on this project. Okay, so let's dive in. So once again, recall the problem of ill-posed image reconstruction. We've talked about so far, we have some sort of image X that we would like to recover from our noisy measurements Y, where it's degraded using this forward model. So we can talk about, black hole imaging is, this ill-posed inverse problem doesn't just appear in black hole imaging, but in many problems that I'm sure all of you are working on. For instance, you might have seen this inverse problem in other forms like super resolution or compressed sensing in medical imaging or denoising. So let's just step away from the black hole imaging problem for a second and talk about just ill-posed image reconstruction in general. And I'm going to talk about it in terms of this denoising example first, and then we'll come back to the black hole later. Okay, so in ill-posed image reconstruction, we lost information through the measurement process. So we have to use priors or regularizers to recover that back again. And remember, this is that equation I showed before of maximizing that posterior probability, which you can separate into your likelihood and your prior. And so we normally build in some sort of model of what images look like in order to recover an image back in the end. But we wanted to ask the question, how about if we were given only noisy corrupted measurements and a possible set of image priors? Are we able to select the best prior to use for reconstruction? So we don't have to decide ahead of time which prior to use, but the data tells us which is the best prior. And what do I mean by that exactly? So for instance, by just looking at the data Y here, can we tell, can we say, and we don't know anything about the underlying image structure, I want to be able to select the prior that I should use for doing image reconstruction. So I don't know what this image looks like. I don't know what class of images this data comes from. I just want to know, when I do the image reconstruction, can I select what prior I should use? So for instance, let's say I was given 4 prior models, one that characterizes zeros, one that prefers images of ones that prefers images of 2s, 3s, for instance. So we have these 4 models. And by just looking at the data alone, I want to select which of these models I should use for the image reconstruction task. So a natural approach would be to find or select the model that maximizes the probability of a model given the measurements, right? So I want to maximize the probability. I want to choose the model that maximizes the probability of that model given the measurements, okay? And this seems really hard to solve, but again, let's use our handy Bayes rule. We can separate it again into these terms, and we can write that instead as the probability of the measurements given the model, and then the probability of the model. The probability of model is easy to compute. We can just say it's a uniform. We don't have any preference for any of these models. And then all we care about is this. Characterizing the probability of the measurements given the model. But unfortunately, computing this is still intractable. And that's because we have to say for a given model, we have to sample every possible image that could come from that model and then integrate all over that whole distribution of images. And this is intractable to do. So our work, though, we've shown how this can still be well approximated by something called the evidence lower bound. And to understand how we can use that and how, let's dig in a little closer. So let's say we wanted to be able to recover a distribution of images constrained by only a certain set of measurements. So let's say we have these measurements, we want to recover that posterior probability of possible images given this measurement under, for instance, the model that the image is a picture of a 2. Okay, and recovering this is called, as I said, the posterior probability. And this is a hard thing to do in general, especially for high dimensional imaging problems, because you have so many parameters that you're trying to recover. So instead, what people often do is something called variational inference. And what is that? Well, in the goal of variational inference is to find the parameters of a simple distribution, we're going to call that Q phi here, that kind of approximates this really complicated distribution, the true one. So in particular, we define this family of density functions Q phi, and we say, let's optimize the parameters of phi so that it best matches this really complicated posterior distribution. And oftentimes the way that you do that is by optimizing something like the KL divergence between them, which basically measures the similarity between these 2 distributions. Okay, but if you actually write out the KL divergence, you can you write it in terms of these 2 terms. One is called the elbow, and you don't have to worry about what it is exactly right now, but no, it's something easy to compute once we've optimized for the variational distribution. And the second term is this log probability of the measurements given the model parameters. And so normally we only have one model, like we only have like one prior model that we're using when we're doing the posterior estimation. And so people usually just ignore this term, but actually like this is the term we're going after, right? We want to know what the probability of those measurements are given the model. And so, so we're after this now, okay? And that's cool. So how should we compute it? Well, if we did a really good job of estimating this variational distribution, then this KL divergence, remember, this measures the similarity between, and if it's closer to 0, it's a similar distribution. So if we say we did a good job getting the variational distribution, this should be close to 0. And so then you can just simply rewrite this log probability of the measurements given the model as this elbow, which I talked about as being something that was simple to compute pretty easily once we actually have solved this variational distribution. Okay, so that's great. So what does that mean? So that means that going back to our original problem, if we want to find the best model that explains the data we see, and we don't have any preference for any particular model here, so I'm just going to rewrite this. This is measurements given model. It's the same thing, measurements given model. Then all I have to do is estimate a variational distribution under each of these models. So I solve what's the reconstruction problem here under a model of zeros, under a model of ones, threes, fours. I have 4 variational distributions. I estimate the elbow under each of those variational distributions. As I say, the best one is the one that maximizes that elbow. Okay. And by doing that, we can see that the model in this case for ones maximized that elbow. And it actually was the case that this one actually came from this is a noisy image of a 1. Okay. So let's try another simple example. So here's an image of 2s. Again, I saw a variational distribution under each model, a model of zeros, ones, 2s. And here I'm throwing the mean of the posterior reconstruction. So you can see, like, for instance, the 0. Here's the noisy image. The 0, it tries to make this 2 looking thing into a 0, right? But if you look at the elbow, it selects that the model that it had the most evidence for was the 2 here. So this maybe isn't too surprising, because if I showed you this picture, what's the way you would solve the problem I posed? Well, you'd probably do in your mind a reconstruction problem. You'd say, okay, what if it's a 0? What's the reconstruction of 0? What's the 1, 2, 3? You'd probably do each of these and you say which one fit the data best, right? And that's pretty much what the elbow is basically trying to quantify. But how about this one? What if I gave you this? Well, what's this number? I mean, maybe it's an 8, maybe it's a 3. It's really hard to tell, right? And in this case, it highlights that the elbow would have a similar confusion. So in this case, it basically says that a 3 and 8 both have very similar negative elbows here. And so it slightly ekes out on preferring an 8. The real one ends up being a 3, but it would have a similar confusion as us, right, in selecting the model. Okay, so getting back, so basically, hopefully I got the main point across of, by using this thing called the elbow, when we do this reconstruction problem, we can try to find what prior had the best evidence for us to do the reconstruction problem with. And so getting back to the black hole problem, perhaps rather than blindly applying different image priors and then seeing how they perform on synthetic data only, perhaps maybe we're going to take our data and we could score under something like the elbow, how good that particular prior model is, how much evidence there is for that prior model under the data, and then weight them according to that. Here we're asking still if we could select among a discrete number of priors or prior models, but instead I want to say, can we solve inverse problems without any predefined prior? So how might we use what we just learned to do that? And it turns out that we found that in some cases we can. The key insight being that common structure across independent problems can be sufficient regularization alone. So what do I mean by that? So again, going back to the black hole problem, remember that our black holes are both evolving. Sagittarius are much faster than M87, but they're both evolving. And thus far in all black hole reconstructions, we've hand-designed priors in doing the reconstruction, but we used a large collection of them, but they were all still hand-designed. So I want to say, can we not hand-design them? Can we just learn a prior from just the data and use that for the video reconstruction task? So remember, at a single instant at a time, we're going to collect some measurements. I'm just going to represent these measurements using the inverse Fourier transform of the zero field reconstruction. So you get like this noisy kind of image here. But now we no longer have one set of measurements, but we have lots of measurements over time. And these all come from different images of the black hole, but they all share common underlying structure. And so we want to leverage that knowledge that the measurements share common looking underlying images to solve that inverse problem. And the way we do this is by learning a single generative neural network that models a type of image that all the independent measurements thinks is a likely image. So basically, each of the inverse problems from every instant in time wants a particular prior model. It prefers a certain prior model, but every problem has a different underlying image. So they all want different prior models, but basically they try to form a consensus towards what is one model that works well as the prior model in all these inverse problems. And I'm happy to dive into the deeper into these, but for sake, I'm just going to time's sake, I'm just going to skim over and show a few results. So we've been able to show on realistic black hole imaging problems that we can reconstruct cleaned up black hole videos when we only have access to the noisy measurements. So again, the key insight being here is that they share common low dimensional structure. There's the same ring structure in all of them, but the fuzzy stuff, the wispy stuff is changing. But we want to say, it's really hard to see here, but it actually does recover a ring structure here from all these noisy measurements alone. And again, there was no explicit image prior used here. It inferred an image prior that it then used for image reconstruction. And again, you might think that this reconstruction, it's hard to see, but there is a ring here, but you might think it looks pretty blurry. But remember, we're working with, this is really the intrinsic resolution we hope to be able to capture. So it's able to get that kind of. Also, I want to mention that I kind of use this visualization of the measurements for visualization purposes, so you can see there is some shared structure there, but actually the measurements actually look something more like this because we lose our phase due to the atmosphere. But there is underlying structure there that is common across all of them, and it uses that with knowledge of the forward model, of course, to recover that shared structure generator that it can use for the inverse model. Okay, so even though we've only applied this to simulation so far, in the M87 case, we're currently extending it to Sagittarius A, and I'm really excited for the future of how this might be useful for when paired with the next generation Event Horizon Telescope in doing video reconstruction while trying to reduce our bias from human-imposed priors. Okay, so great. Now I've talked to you about some work in how we can do video reconstruction with weak assumptions, weak constraints, the only constraint being that there is some shared structure in time, nothing about the actual structure itself. But what happens when we really strengthen those assumptions? So for instance, let's say we assume general relativity is true, or the emission model of how what light is doing around the black hole. We know that emission model. And with these stronger constraints, we can make even a clearer movie, or perhaps something even more crazy. With the help of computational methods, we can recover the emission not just in 2D or as a 3D movie, but actually see it moving in 3 dimensions. And this imaging capability would be able to not only just tell us about the dynamics of the accretion, but also kind of maps out space-time itself. And so I'll show some results of this first in simulation, and then in the end, I'll actually show results that we've applied this to some real data. So it's showing the first 3D reconstructions of emission moving around a black hole, of course, with lots of assumptions imposed in it. So how do we go about seeing these hotspots spiraling around the black hole in 3D? Well, we face 2 big challenges that sets it apart from your typical tomography you might think about like with CT or 3D reconstruction. First is that, remember, in our case, the rays move in curved lines and can even go in circles around the black hole. So that's challenging, but it's actually not that big of a challenge. The big challenge is that typically in tomography, you have views from all different angles. Like in CT, you get different projections of the body from all different angles, or in 3D, you have different camera viewpoints. In our case, we only have the gravitationally lensed projection from one orientation in the sky ever. We're never going to see other orientations of the black hole. We're only going to be it from this direction. And in fact, we have less than that. We only have sparse measurements of that projection over time. But recently, we applied an approach where we're able to show that on these problems, we're able to take these sparse measurements and use them to recover back the 3D structure of where the hotspots originated in a video. So how can we do that? Well, we inject some of the expected physics back in by saying, let's say we trust general relativity, but nothing else. We don't know what the actual 3D structure looks like, but we trust how material is moving around the black hole, how light bends around the black hole, and how it's emitted around the black hole. If we trust those things, then we can go into 3 dimensions. So Aviad Levis, who is a postdoc in my group, going to be starting at University of Toronto soon, has been leading this effort, but also with our collaborators at Google, Princeton, both within the EHT and within computer science. So this is really a interdisciplinary effort. And I don't have time to get into the details, but just to give you a rough idea, we take inspiration from the very popular work that I'm sure some of you have heard about, these neural radiance fields in computer vision. And we build this end-to-end deep learning system that says, I have some measurements here, and I have a model for how certain measurements at a time would propagate over time. I want to use a neural network that parameterizes 3D field, such that if it was propagated in time, would lead to the measurements that I see. And so we can recover what that 3D distribution looks like at some initial time 0. And this is all trained jointly. And by using this network, we show that there's promise in using such an idea to recover the dynamic flares exhibited by Sagittarius star over short periods of time with something like the next generation Event Horizon Telescope. So you might ask, like, why is this useful? You put all this physics back in, like, it's like you're building this huge model. So what are you actually learning? Well, what we're learning is that we don't have any constraints on what the actual structure of the emission looks like. So we're still completely agnostic to that. We can get random things. So for here, we have the digits 0 through 3 rotating around a black hole. Obviously, like, we wouldn't expect to see that, but we're not restricted to having very particular like hotspot models of what the structure looks like. Here we can recover these generic kind of distributions around it. And so this is really early stages, and we don't have any measurements from the NGHT yet. But although getting results like these may seem like really far away, we've actually started using a slight modification of this method to see dynamic behavior close to our black hole already. So how? So the image that I showed you before was an image recovered from data taken on April 7th, 2017. And although on that day the black hole was burbling around, it was actually relatively quiet. It was moving for sure, but not making like big explosions. But actually on April 11th of that same year, the Galactic center seemed to be explosive. And we saw this signature of this flaring behavior that could be caused due to the presence of flaring hotspots rotating around the black hole. So these bright spots that start moving and shearing out around the black hole. And how do we know? Well, we collected data from a telescope in Chile called the ALMA telescope. And in the ALMA telescope, the data is not good enough to make a picture, but what you can see is these like little, this structure, this periodic kind of structure that indicates that maybe something seemed to be moving around the black hole. Of course, it doesn't say what it is. It just seems like there's a hint to something is there. So what is that? What is the data that we use exactly? Well, it's called a light curve, which is just a fancy way of saying the integral of all the light over time. So in other words, we talked before about the projection. Remember the lens projection of the light around the black hole that we'd see from Earth. In this case, we're basically summing up all the pixels in that video as a single pixel and playing it over time. And that's your light curve. But we actually get a little bit more than that. The light curve that you get by doing this would just be like watching the black hole with regular glasses. But instead, we see the polarized light. So it's like you took your 3D polarized movie glasses and you watched the black hole once with one eye closed and once with the other eye closed. And getting that polarized light allows us, has really, so why is that important? Well, the polarized light has really strong signatures for something like a hot spot that would be spiraling around the black hole. And so we can show that we can take these measurements, these polarized light curve measurements, and use it to try to recover back the structure of those flaring hotspots that have a very strong polarization signature. And you might wonder, how is this even possible? Because it's kind of like taking your favorite video, taking every frame in the video, summing up the pixels, playing those pixels over time, and then trying to say, I don't want to just recover the video of the movie over time. I want to recover the 3D structure of the characters over time, which seems like it's absolutely insane. And it is in this case, and that's because we don't have any strong physics constraints. But in our case, we have very strong physics constraints about how the emission might be moving, how the light is bending, and how it is emitting the polarized light. And so by using that, we can actually reliably often recover the structure of the initial hotspot. So here, for instance, is a simulation that mimics kind of the data we got from the ALMA light curves, and we can see we can recover the location of the hotspot initially, but it doesn't just have to be a single hotspot. We can have other kind of geometries that we recover. And so using this approach, we've already run it on the real black hole data collected from the center of our galaxy. And we see that even though this is a super ill-posed problem, we can often recover the actual same basic structure. So we recover two hotspots that are roughly like 75 billion kilometers. Okay, pause it here. So this is at some initial time at 9:20 UT on the April 11th. We see that there was this structure of these two kind of bright spots, or something that was roughly in this region, about 75 million kilometers from the black hole. And this was a very strongly polarizing structure that when it sheared out over time, as we're showing over here, according to some physics model, matches our light curve measurements that we had. And of course, this is very reliant on the model that we have, what we see by testing. But that model is, one is it's motivated by other people's work, but also when we change that model, we don't see the data fits as well. So even though this is still a super ill-posed problem, and you kind of need to make sure whenever you look at it, you take into account completely all the model assumptions, it's pretty exciting that we're able to start to recover something about the 3D structure of the environment around the black hole. Yeah, so I just want to mention, you know, there's a lot of uncertainty, but still super exciting to me. And I hope this shows, you know, there's still so much more to come. And although we've learned a lot from the images of Sagittarius Star and M87 already, what I hope I got across in this talk is really we're just at the beginning. There's still so much more to come. Hopefully one day we'll not be able to just show you a still image of a black hole, but a movie, perhaps even in 3D completely, without all those strong physical constraints. And the main message, though, I really hope I got across is that computational algorithms play a key role in the science that we've done. And but it's really, we're just at the tip of the iceberg. And I hope you keep this like two-way street in your mind as you go forward in the future work, as we're trying to solve these problems from both directions. And so with that, thank you. I want to thank the entire Event Horizon Telescope collaboration for the amazing work that they do. I have the privilege to work with them on a daily basis. In addition to Aviad, who led the 3D tomography work, and then Oscar, Angela, and Yvette, who did the previous work. So thank you.
Thank you, Katie, for this wonderful talk. I'm sure you've got a lot of ideas that we can discuss later, maybe. So do we have questions? Yes.
So if I understood correctly, you were talking about images or movies taken over a single night. Used to reconstruct this image of the black hole. Does it make sense to get knowledge from many nights of measurements?
Yeah, that's a great point. So the challenge with Sagittarius Star is that it was moving so quickly that we had to take into account its variability over a single night. But with M87, over the course of a day, like from day to day, you actually might see a little bit of motion. But within a single night, it's pretty much still. So we can do image reconstruction pretty well with just one night of measurements. But that is one interest for the EHT going forward, is that can we take data over longer periods of time of M87 and then use that to reconstruct a movie where we feel a little bit more confident in the structure. The challenge is actually taking this data is a huge thing. You know, people have to travel to telescopes, and it's a huge amount of effort, and you also have to apply for time on the telescopes. So it's usually we get about 1 week of time a year. It's challenging to get a large amount of time, and also you have to be able to operate these telescopes remotely. So that's definitely actually one of the big interests from here at Arizona, is being able to do this so that we in the future we can make movies without having to deal with just Sagittarius Star's rapid time variability.
Your data necessarily live on a very complex feature space, right? So it could be disjoint manifolds all over the place. How will you, or are you attacking that? Are you injecting that kind of prior into your model so that you're actually dealing with, these disjoint manifolds?
Yeah, maybe I'm not understanding your question exactly, but definitely the problem that we solve. So I talked about it in terms of the measurements that we make as being kind of samples from the Fourier transform, which itself is linear. But actually, because we lose the phase of the measurements due to the atmosphere, we actually have to solve basically a constrained phase retrieval problem, which ends up being a non-convex inverse problem. And therefore, the images that the posteriors, the probability of the image given the measurements does not necessarily need to be one like nice single mode posterior. Sometimes you'll get multimodal posteriors where different image structures both correspond to the data, and it's really important that we actually recover both of those. So yeah, we spent a lot of time on like the methods that in the EHT so far have been trying to use different image priors and different models to try to search that space to make sure we captured the all the different possible distributions. But also we're interested in developing variational inference methods and sampling methods that work on these high dimensional spaces that allow us to quickly recover this without having to do like what we had to do here, which was huge parameter surveys that took lots of people hours and lots of compute resources. So yeah, that's definitely something of interest. I don't know if that answered your question exactly. Yeah.
Hi. So from what I'm just seeing with the Event Horizon Telescope is you essentially have like the largest aperture possible. So like
On Earth.
there are so like apart from black holes, are there like other potential like objects of interest that you could image? Like it seems like you'd have to have like a lot of radio emission coming from it, but yeah, so
definitely the Event Horizon Telescope also images other active galactic nuclei where you can't actually see that ring itself, but you see these massive jets, galactic sail jets coming off of the black hole. So we image like these other structures that are also black holes, but not this, they don't look exactly like this because you're not seeing that ring structure. I think it's also an interest, actually other people in the audience can probably answer it better. You want to go, Remo? I don't know if you have anything. Yeah.
Operations managers, Event Horizon Telescope. So one area we're branching out to, and we're actually trying to observe that this year in April, is to look at maser lines. So that's very compact emission. It's microwave lasers, right? So they're very, very bright, very compact, and we should be able to see them. But this emission is broadband emission, so you observe it over very large frequency range, and we collect that. The technique that we had to develop is to do the same thing over a very small frequency range because they're very narrow lines. So that's common.
Thank you.
And by the way, keep an eye on 2026 because I'm pushing for a movie of 2026, M87 in 2026. At least taking the data, then it will take us years to
Yeah.
to publish the movie.
That's very exciting. Yeah. We have a question here.
Hi.
Hi.
Go Beavers. I'm from the Dr. David Brady Lab.
Oh.
Great talk. I just kind of had a question about your priors.
Yeah.
When you introduced the astronaut, you talked about how space-time, the wave vectors are curved in space, but it's well known that when you use NERF, it assumes a projection geometry where the rays aren't straight.
Oh, we modify it so that you can change so that's actually the easy part. You can take NERF, which assumes straight rays, and you can just say, if I know how they're bent, then you can just have those bending rays. So in this work, we assumed, we knew the black hole's mass. And if you know the black hole's spin and mass, you actually know what those ray paths are. So we know the Sagittarius star's mass pretty well from other measurements. The spin we don't know. So what we did is we looked at it, we calculated what the ray path would be for the same mass, but all different spin values, and then solved the reconstruction problem under each of those spin values, and we saw that it actually didn't affect the reconstruction that much. So we always kind of got the same, the exact structure per voxel structure is different, but it generally gets those two blobs in the same location, no matter the spin. But that was assuming that we did this like brute force search over spin. We have some other work where when we modify kind of NERF where we say for other things like weak lensing, when we're wanting to recover dark matter fields, where actually it changes the thing that we're recovering changes the path that light takes, but because it's NERF is differentiable, we can do that. But yeah, in this case, it was just a fixed ray pass. We can just change NERF to have those curved ray pass instead.
The main prior question, when you call it prior free, when you use your measurement data to create these priors from the different problems, did you use the same measurement data across the problems?
So we assume in that case, it was, you have to assume something is changing. So either you assume your measurement forward model is changing or you assume the underlying image is changing. But you need to have something changing. In this case, the forward model, I think, was the same because we were assuming M87 over different nights. So it has the same basic measurement pattern, at least, like which frequencies you collect, but the underlying image changed. So there's differences in the measurements that we get because of that, but it tries to find a consistent underlying representation of the low dimensional structure across all those measurements. Did that help clear what?
Spectral bias since the entire system.
I'm not following. So if what is constant across the system?
What's the spectrum is maintained?
The forward model, yeah. So which frequencies you collect, yeah.
Yeah.
And you're saying, does it have a bias towards something that like kept? Yeah. So it would if you have very, very similar. If you only have one image, underlying, if it's so low dimensional that it's one image, then it doesn't learn anything. You have to have enough variety, things going behind it. Or you have to like strike that balance of enough things that you get like the measurements cover a wider range. So it tries to like piece out. It tries to distill out what was the common part across all these measurements. I don't know if that helps explain it. Yeah.
Okay, I think we can still take one or two questions. Yeah.
You said something is varying about the black hole or its environment rapidly as you're taking those measurements.
Mm-hmm.
What do you know about the things that could vary? Could it be like a binary black hole, for example? Or do you know that it is a solid or spherical or something? What do you know about it that you put into your priors?
Oh, so what do we put into priors about how it's varying, you're saying, or what is varying around the black hole?
Black hole?
Oh, so in this case, these are not binary. This is just a supermassive single black hole. But around it is this hot gas that's like heated to hundreds of billions of degrees. It's kind of spiraling around it. Actually, CK, who's sitting right next to you, really knows all the details of this. He does simulations of these, so you should talk with him. but but anyway, yeah. So it's kind of like this gas that's spinning around. It's not, but every once in a while you have these like low density, high temperature regions that people have predicted form that are these like flaring structures, but there are still like kind of predictions, like there are simulations of what they might look like, but kind of no one has seen their actual structure before. So that's kind of what we were after. And so in the actual model, what were the assumptions that we made? We assumed a velocity profile for how material rotates roughly around the black hole based on its orbital, on its radial distance. We assumed we had synchrotron emission, so it had some sort of polarized structure to the emission of the hotspot that was, and the other stuff around it is kind of depolarizing because it has polarization everywhere, so it kind of doesn't have a strong polarization signature elsewhere. And we also assume the black hole mass and the which gives us those curving rays from general relativity. So those were the assumptions we made.
Last question. Yeah.
So when you're replacing the assumption of spatial priors with assumptions about the variability and propagation forward in space and in time, how much are you able to reduce the degrees of freedom in the assumptions so that you're getting, starting to have more satisfy Occam's razor and explain it with a simpler assumption?
Okay, so you're saying when you we have this insanely ill-posed problem, right? Of like, we only have we have two light curves over time, right? And from that, we're trying to recover not the 2D structure, but a 3D structure, right? So it obviously has a lot of the physics does a lot of constraining for us. I think that it's hard to say exactly degrees of freedom, but what we do is we like reinitialize with different and see like kind of the space of possibilities, and each one does get a slightly different answer every time we reinitialize, but they all kind of got similar with like this black hole thing that I like to show, where they all kind of look different, but they all kind of most of them have that ring structure. It was the same in the other case where it was constraining enough that each one the volume looks different, but they all kind of had the same kind of hotspot appearing at the same location. Yeah, based on just the physical assumption. Yeah. Actually, there's also some smoothness assumptions implicit into the neural network. Because we use a neural network to represent the volume, it prefers smooth structures. So there is some implicit regularization there as well.
Okay, so our speaker will still be around for like a couple of minutes after the talk. If you have remaining questions, you can ask her directly. So let's thank our speaker again.
Thank you.
Maybe we have this nice certificate for you with a little optical sciences fee that you can wear on your flight.
Oh, thank you. Oh, thanks. Thank you.